Okay, so what we're doing today, I think, is pretty simple. 1.4 functions. So one way of thinking about a function is that you have some set A and you have some other set B. So you have sets set A and set B. And a function is some sort of a rule, some sort of a construction or a rule, which assigns to each x in an element denoted f of x in B. So if you're calling the function f, then for each x here, it'll associate some element f of x in the second set. Okay. I'm sure that's familiar to you, right? I remark that so it takes in something, and spits out something. In a consistent manner. Right. What's called in a well-defined manner. Okay. So it doesn't like if you have a function, it's not arbitrary. It's not whimsical, right? It's not like I'm going to feed the function some number, and if I feed the function the number 1, it won't sometimes say 5 and then sometimes say 2, right? It will give the response. If you feed it the same thing, it'll give you back the same thing. So this is what's called well-defined. Okay. So just some terminology. Actually, just call this notation. Some notation. If I write something like this, f goes from some set G to some set R. F, different arrow, f of x. So here's the notation. Sarah, do you have can you not read something?
Right before it takes in something, what is that?
Remark. Sorry. Yeah, Isaac.
A construct rule which assigns
to each x in A an element f of x in B. Maybe I should say to each element x in A, although it's clear from the notation, an element f of x in B. Okay, so if I write something like this, the way you read it is f is a function from domain D to range R, assigning to each x in B and f of x in R. So that's the English equivalent of this brief package here. Okay. So just for example, you can have a function going from the collection of math 30 students to the letters A, B, C, D, F. Right, here's a function. At the end of the term, I will have a function. I'll create a function that maps each student to a particular letter. right? That's a function, right? Going from the student to the grade of the student. Okay. Another example, could talk about function from the non-negative real numbers into R, taking x to the square root of x. Okay. So this is how you describe the square root function, right? Its domain, right? The numbers that it will accept, are the non-negative numbers. You don't feed the square root function you don't feed the square root function negative numbers in this course. You do later, right? And so it takes in non-negative numbers and it gives you back some real number, right? And x gets mapped to the square root of x. Let me remark that we're always going to use this. Will always be the positive square root, the non-negative square root. When you write the square root of x, that's always going to mean, if I write the square root of 1, I don't mean -1, I mean 1. Okay, and so so this is the standard notation. Yes, Nora.
Sorry, what does it say after always denote?
We'll always denote the non-negative square root, the non-negative square root. Okay, so this is the sort of standard notation, but people usually don't write it out in this way. Usually you just write f of x is square root of x. Okay, and what you just, so you don't specify the domain, and you sort of think of the range. You sort of figure out what the range is, right? So you do more work on yourself. The domain is assumed to be as large as possible. Okay, so abbreviation. So instead of writing this, you write this, and you just assume that what is the biggest set of numbers that you can feed in here. Well, it's all non-negative numbers, right? So you just assume that's going to be our domain. Okay, it need not be, right? We could say, I'm only interested in the square root function starting from x equals 100 and onwards, right? That's a different function. But if you wanted to specify it, well then you probably write things out this way. Okay. But if you say something like this, you're not going to say, oh, does he mean x is greater than 100? No, you just assume that the domain is as large as possible. Take the maximal domain you can think of. Okay. Is that clear? Okay. Okay. So let me say something about the term range. Comment about range. Okay. So in this previous example here, I said that the range is R, right? I said the range is R, right? And that's certainly true, right? The square roots of non-negative numbers are real numbers, right? But could I say something else here for range? What else could I say here for range? Could I be, suppose I say they are complex numbers. Is that okay? Would that be an okay range? Are the outputs complex numbers? Well, actually this would be okay too, because the real numbers are contained in the complex numbers, right? So that would, if I wanted to say the range is the complex numbers, that would also be valid, right? Wynn, what were you going to say?
I was going to say it would be all positive numbers too.
Right. So you could also say non-negative numbers, right? That's also valid. And in fact, that's in some sense that's the best answer, right? Because that's exactly what you get, right? If you look at the square root function, right? Then if you look at the square root function, then what kind of things do you get back? Well, at 0 you get 0, and as you feed it higher, bigger and bigger numbers, you get bigger and bigger numbers, right? So you get everything from 0 onwards, right? So in some sense, this is the best answer, right? Because this is really what you get. This is really the collection of all outputs that you get handed back to you, right? Okay. But the range, if you're talking about range, then actually all three of these things could be range. Okay. Okay. So range is a little bit imprecise. The notion of range is somewhat imprecise, right? Because there's all the range just means a set that contains all the outputs, right? So could be defined in different ways. Could be defined in different ways. Okay. Could be different sets. Okay. Now this thing is actually something called the image, right? The collection of all outputs of f is called the image of f. Okay, the image of f. So it's all, right, if you have some f going from B to, f going from A to B, then the image of f is all B in B, where B equals f of A for some A in A. Right. Maybe some of you in the back can't see it, so let me write it up here. The image of f is all, so f is going from A to B, is all B, the set of all B and B, where B is f of A for some A in A. But in English, this basically just says the set of all outputs, the set of all outputs of f. So, to give a silly example, at the end of the term, like I said, I'm going to make this function f, like sort of ominously named f, that takes each student to a letter. Okay. Now that function, whatever it is, right? This is its range, right? This is its range. Or you could say, I could even put the whole alphabet here. That would also be its range, right? Because the outputs certainly lie in the alphabet, right? But I'm hoping that the image, doesn't include some of these letters. Okay, is it clear the difference between range and image now? Right? The image of that function will be the outputs that it gives me, right? The outputs. Okay, the actual outputs. Okay, example 3. Suppose I have a function like this. Okay, it goes from the non-negative numbers into the reals, and it takes x to x over x plus 1. Okay. I'm going to ask you, what is the image? I'm going to ask you to think about this one. What's the image of this function? Okay. So take 2 minutes and see if you can figure out what the image is. Okay, talk to somebody nearby and see if you can come up with something. If you have
No, like I can't go into
Okay. Would anybody like to say anything about it? Should choose somebody at random? Do I have it? I don't know if I have a die. I don't have a die. Don't remember your name. What's your name? What's your name, please? Yes.
Marine.
Marine. Thank you. What do you think?
I was getting fractions greater than 0.
Fractions greater than 0? So, okay, so you say, well, the things that I'm putting in here are all non-negative, right? So whatever my numerator is, it's non-negative, and my denominator is also non-negative. Okay. So say, okay, at least I'm getting things that are so maybe it's numbers bigger than or equal to 0. Right. Certainly, that seems like that's better than what we have, right? It looks like the way it's written, it looks like you could get negative numbers. In fact, you can't get negative numbers. Okay. Anyone want to say more? Anyone want to say more? Shannon, how about you?
That's as far as we got it.
Okay.
Because you can't literally, like, no matter what you put in, it's just going to continue to be a ratio.
Okay, it's going to be a ratio. Let's look at this ratio, right? You've got x over x plus 1, right? Could I get the number 2? No, why not?
Because it will always be a number with that number plus 1. So
Yeah.
So
The denominator is always bigger, right? And so, people, those of you who have your hands up, I think you're all itching to say it. What? But go ahead, Rena. Rena?
It would be like the number would be less than. It'll always be less than 1.
Less than 1. Okay, so you know that the output, right? It's going to be the outputs, right? F of x always is going to be greater than 0, and it has to be less than 1, right? It has to be less than 1. So that, at least we know, could it be equal to 1? No, you can't, because the bottom is bigger than the top, right? Let me ask you this: do you get everybody between 0 and 1? Do you get everybody between 0 and 1, or just what you just told me is that the numbers you get are between 0 and 1, and I'm going to ask you, do you get every number between 0 and 1? Suppose I say like 0.8. Do you get 0.8? So maybe that's the question. Can you get 0.8? Can you get 0.8? Sure. If you feed it a 4, you get 0.8. Okay. Can you get all numbers between 0 and 1? Can you get all numbers A between 0 and 1? When you're saying no, why?
Because that's infinity, and even though you can't go to infinity, it's getting closer and closer to 1. So the numbers like
What's infinity? When you say that's infinity, what's the that?
the numbers in between 0 and 1.
There's an infinite number of numbers
Infinite,
between?
yeah.
Okay, but you've got an infinite number of inputs here,
Right.
so why, there's going to be an infinite number of outputs. So
There'll be more outputs as you get closer to 1.
more outputs as you get closer to 1. Oh, so you're saying that they sort of bunch up.
Mhm.
They bunch up. Oh, that's great. That's great. Certainly they do bunch up. They do bunch up. Nico.
You can't get all of them because if there's you can't get the irrational numbers.
Can't get the irrational
0
numbers.
and 1 because it's set up like that definition of function is like a fraction, so then you can't express irrational numbers as a fraction.
Okay. So you're saying, well, look, this looks like a fraction, a ratio. So maybe the outputs have to be rational, right? But remember that for it to be rational, the x would have to be rational.
Oh, so you can.
So if you feed it an irrational number, you can get out an irrational number. So that's actually okay. You can get irrational numbers out of it. But that's a good. That was good thinking. Wrong, but good thinking. Okay. So let's just think about it. Let's figure it out. Let's pick an arbitrary number. Y. Let's do it this way. So earlier I said 0.8. Can we get 0.8? Right? And maybe one way to think about it is like this. You say, well, is there an x such that x over x plus 1 equals 0.8? Right? And then what would you do? You'd figure out what x is, right? By just using your elementary knowledge, right? So you'd say, well, 0.8 x plus 1. In that case, 0.8 x plus 1 would have to be x itself, right? And that tells me that x is going to be 0.8x plus 0.8, right? In other words, moving this to the other side, 0.2x equals 0.8. Right? By junior high school math, right? And so you get x is equal to 4. Okay. Okay. So now, is that all right for everybody? Okay. So now let's do that. Can we get the number y? Okay. The number y. So here's the number between 0 and 1. I'm going to call it y. Okay. Okay. And you can think of this as it's just like a general number. It's one of the numbers between one of the numbers between 0 and 1. Yeah. Julie.
Aren't there like the same, or can't there be like the same amount? Because you're saying that it bunches up closer to 1. But if you were to use fractions like 1/2 and stuff, can't you produce like a large bunch closer to 0 too?
Could, yeah. So, you'll see what happens. Hold on. Okay, can we get just some number y between 0 and 1? So you say, okay, in that case, we would need x. What x would do? What is there an x such that x over x plus 1 is equal to y? Okay. And we play the same game, right? In that case, we need x to be y x plus 1, right? That's yx plus y. And so you would need 1 minus y times x to be equal to y. Right? Just move the yx to the other side. Right? Move the yx to the other side, you get x minus yx. Right? X minus yx equals y. In other words, distributing out the x, 1 minus y, x equals y. And so what x will do for you? What x will do it? You need to take y over 1 minus y. Okay. So, for example, if we're looking at 0.8, right? If y is 0.8, we take 0.8 over 0.2, right? If y is 0.9, you're going to need 0.9 over 0.1, right? And so on and so forth. And what you see is that whatever y you choose, there will be an x that gives it to you. So in fact, we do get the whole thing. We do get all numbers. We can get any y in 0, 1. Right? We can get any y in 0, 1. So the image is all of 0, 1. It's not just that the image lies inside there, but it's the full interval here. Amanda.
I just got a bit confused about the notation. What does it say y equals, is it 19? What does it say?
0.9.
Point.
Okay. So in fact, for this function, you can figure out what the image is, and it turns out to be the interval 0 to 1, including 0, but not including 1. Any questions? Yes, Shannon.
If we couldn't get, like, if that wasn't true,
Yeah.
what would it would have ended up like? Would you just not isolate x? Like, how would you know that it doesn't work?
Yeah, it would have been, like you would have ended up, there would have been some, like you could have a function where like some numbers are not attainable, right? So for example, right, like we already know we can't get 1. Let's see how we can see that. Okay, is there x such that x over x plus 1 equals 1? Okay, let's solve that. We'll see how it messes up. Okay, well then we have x equals x plus 1. Right? And so we have 0 equals 1. Okay. We need, to solve this, we need an x that shows us that 0 equals 1. Okay. There is no x that will do that for us. Right? Okay. Yeah. Okay. Okay. Okay, a little bit more notation. Something very easy. Any other questions on the image? The difference between image and range. Okay. So a little bit more notation. there are things called piecewise-defined functions. Piecewise-defined functions. These are functions where, on each different piece of their domain, they have a different definition. Okay, so here's an example. There's something called the signum function. Signum function. Okay, and the way that is the way that's notated is 1 if x is bigger than 0, 0 if x equals 0, -1 if x is less than 0. Okay, so you see how this is, right? Here's the function on the domain, on this part of its domain, on the positive numbers, it gives you a 1. On 0, it gives you a 0. On the negative numbers, it gives you a -1. Okay, so it's piecewise defined, right? On this part of its domain, it has one definition. On this part of its domain, it has another definition. On this part of its domain, it has another definition. Okay, that's it for piecewise defined functions. That's, we can make up more examples, but they're all basically the same, right? You could say, like, I have a function that is, the square root of x if x is bigger than 0, and it is, I don't know, x squared if x is less than 0, right? A function defined in parts, a piecewise defined function. Okay, that's all there is to this concept. Okay, more important, graphs and functions. Graphs and functions. So for a function, a function is a map. It's a map, right? It takes what's called a map or a mapping from one set to another. Right, goes from one set to another set. Maps a point here to a point here. Right. So maybe it's hard to visualize, but for functions going from the reals to the reals, we have a useful visualization of its behavior. Useful way of visualizing its behavior. A graph. Its graph. So, given a function going from R to R, say, we associate with it a set. It's this set, x, y in R squared, where y equals f of x. It's called the graph of f. So in English, right, it's the set of all points on the plane. So it's the set of all points x, y on the plane where y is f of x, right, in English. So just as a simple example, if we have, again, the square root function, right? What does a square root function look like as a map? Right? As a map, if we think about, if we try to represent the square root function in terms of arrows, say, well, it takes 0 to 0, right? The square root function takes 1 to 1. It takes 2, well, 3, 4. It takes 4 to 2. It takes 9 to 3, right? 9 goes to 3, right? And so on and so forth. And you'd have to draw an infinite number of arrows, right? And they'd sort of be sloping up more and more. The speed would be increasing, but you draw like these arrows like this, right? Right? You draw these arrows, and that would be a representation of behavior. That's the square root function right there, right? Okay. So instead of representing it that way, you say, okay, I'm gonna, instead of taking R here and R here, I'm gonna take R here, right? This is my domain, and this is my range, right? So instead of putting them beside each other, I cross them. Okay, I cross them, right? And you say, okay, and I'm gonna put, at each, I'm gonna put all the points that have x, y, where y equals f of x. Okay. So, for example, 0, 0 is going to be on my graph. Okay. So 0, 0 is on the graph, right? Because why? Because 0 is the square root of 0, right? 1, 1 is on the graph. 1, 1 is on the graph because the y coordinate is the square root of the x coordinate, right? Right. 4, 2 is on the graph because the y coordinate is the square root of the x coordinate, right? Right. 9, 3 is on the graph because 3, the x coordinate is the square root of the y coordinate, right? So you find all points where the y coordinate. Find points, all points x, y, where the y coordinate is the square root of the x coordinate, right? And you make this, you put all those points down. So here they are. You put down all those points, and they create this. That's the set. This set is called the graph. For some reason, people don't really understand this. You think, oh yeah, the graph, yeah, we know the graph. But for some reason, actually, you don't understand it. So I'm going to say it again. I haven't really found a good way of making it any clearer. But what's the graph? The graph is all points where the y coordinate is f of the x coordinate. Right. So, for example, what's the graph of the signum function? What's the graph of the signum function? Take 1 minute and write it down. Okay, turn to somebody nearby. Turn to somebody nearby and say what it is.
I was just saying how like what
Okay, what is it? Elise, what is it? What does it look like? Here we have a plane. We want all points where y is equal to signum of x.
would there be a line at x equals 1?
At x equals 1. So here's x equals 1. A line.
Oh wait, no, would be, sorry, y equals 1.
Y
and
equals
then
1.
Y equals -1.
Y equals -1. So here's 1, here's -1.
And the line at y equals 1 would be to the right, would you
Mhm.
believe? And then -1, the one, -1 would be to the left.
Mhm.
And then x equals 0, so there would just be a point.
So there's a point here, and this is open, and this is open, right? So you've got a hole here. Yeah, right? Right? Because you want all points where y equals sine x, right? Where the x is positive, right? Where the x is positive, remember, if x is positive, then the sine function gives you 1, right? Where x is negative, the sine function gives you -1, right? So for positive x, the y had better be 1. For negative x, the y had better be -1, and so on. Let me ask another question. Okay. Suppose you have some function. Here's the graph. This is the graph of f. Okay, and this is A. This is point A and point B. Okay, so just a simple question: what's the slope of the line between these 2 points? Take 10 seconds, write it down. What's the slope of that line? Okay, turn to somebody nearby and say, the slope is this. Okay, who would like to, let me call on somebody actually. Jennifer, how about you? F of B minus F of A over B minus A. Very good, right? You say, well, look, the x-coordinate is B. The x-coordinate of this point is B. The x-coordinate of this point is A, right? And this guy is on the graph, so we know its y-coordinate must be f of its x-coordinate, right? Y-coordinate must be f of its x-coordinate. The y-coordinate must be f of its x-coordinate, right? So we know the y-coordinates, and from there you can get the slope. Now you've got 2 points and you get the slope. Okay. Anyone have questions? Okay. Another one. Here is the graph of f again. Okay. And here is the line. Here's the graph of f of x equals x. So here's the graph y equals x. It's a graph of. So this thing here is the graph of f. And this is the line y equals x. Okay? And you start off with a point A here. Okay? And I'd like to know what, you go perpendicularly over to here, so you make a perpendicular line over to here, and then from there you make a perpendicular up. Okay? I'd like to know the coordinates of this point. What the coordinates of this second point? So take 1 minute and see if you can do it. If you understand what a graph is, then you should do it easily. Okay, turn to somebody nearby and say, this is what it is. Isaac?
A after B.
So, are you talking, which point are you talking about? This one? This one? This is A.
Yeah. You want the one next to
I
it.
want the second point.
Okay, now I see.
Anybody have an answer? Anybody like to say something? Let's, Luke? Vice? You guys have like some sort of, yeah, there's an exclamation coming from over there? Like, yeah.
I'll go with him though.
You go with Vice, okay? That's what you decided. Vice is right. That was the exclamation. Vice is right. Vice says what?
I didn't say it.
Okay, okay. Oh, okay. Evan is right. Yes. Go ahead.
Just x, comma, f of x.
So this is A, right?
Yeah.
Okay.
No,
So what's
the other point?
this point here or this point?
The other, yeah, the one that you're asking.
Okay. Let me ask you what this point is first.
That's a, comma, f of x.
Okay. A comma f of A. Sarah, you look really inspired. Yes.
Maybe. We'll see.
Yeah.
Is the next one a plus x comma f?
No. Maybe to make it, let me put in an intermediate point here.
Yeah.
What's this point? What's this point?
A plus X.
Well, right. What's the y? Let me ask you this. What's the y coordinate at this point? F of A, right? Right. The y coordinate is f of A, and this lies on the line y equals x, right? So what's the x coordinate? F of A, right? Right. I should have made it like this is the graph of g of x equals x, right? The x and y coordinates are the same. Okay. So what's this thing here? What's its x coordinate? F of A, right? X coordinate is f of A. What's its y coordinate? No, I don't think anybody said it. Say what you're thinking again, or raise your hands and let me choose somebody. Jennifer. X is just your general variable, right? X is your general variable.
F of x.
Oh.
F of f of x.
F of f of A. Why? Because this is the graph of f.
Oh.
What's the rule of the graph of f? The y coordinate has to be f of the x coordinate, right? This is the graph of f, right? On the graph of f, the y coordinate always has to be f of the x coordinate, right? That's what it means to be on the graph of f. So, if the x coordinate is f of A, the y coordinate must be f of that. Okay. Good. Evan, you get 1 point for the next exam. Good, right? I think I said that at the beginning. If you do something good in class, you get a bonus point. Okay. Okay, so we didn't have time to get to sequences. That's kind of small. We'll do that at the beginning next time. I might have to adjust the homework slightly because we didn't get to sequences. Okay, that's it for today.